right, here is another interesting problem with a uniform rope of mass lambda per unit length. And it's coiled on this table here. And we are moving the rope with a certain mass with the speed v naught in the upward direction. And there is also gravitational forces acting on the rope. Let's find the force that we have to exert in this point here in order to move at the constant velocity v naught. So first of all, mass equals density times volume. But when we're talking about the linear density per unit length, it's instead this lambda times length. In this case, the length y. So this formula. And y, how long is that? Yeah, from the start, y is 0. And as time goes by, we get that y equal v naught times the time t. Okay. And in this problem, we cannot just say F equal ma or something like that. We need to go to the very definition of Newton's second law. And the definition is not F equal ma. It is actually this one here, F equal dp dt, where p is the linear momentum. So it's this derivative, actually, which is the real truth here, and also power of Newton's law. So we are gonna look at it like this, that the p is some kind of p of a time t plus dt minus the momentum at the time t divided by a small infinitesimal time dt. So let's see here, what is p as a function of t? Well, it's m times the velocity, right? And the velocity of everything here is moving at v naught, so it must be v naught. And the total mass here, mt, is given by this formula here, lambda v naught t times v naught, so lambda v naught squared t. So that's the momentum at time t. And at a little bit later, t plus dt, the mass is a bit higher because it's longer. It moved a little bit more. So it will be this at time t, but if it's time t plus dt, then you have t plus dt here, and you get two terms. And then multiply with v naught, so you get lambda v naught squared t plus lambda v naught squared dt. And then we take the difference, these terms minus this term, so you're left with that one only, lambda v naught squared dt. And then according to the force law here, we will also divide by the small infinitesimal time dt. So this will be divided away, and we have just proven that the force that is lambda v naught squared. So this is the real deal, how you actually should do things, not just taking formulas from the book, like F equal ma or something like that. This is the very definition. So, okay, in the picture we see there is also gravity. Okay, we need to deal with that as well. And then you have a certain mass here, and all these mass elements are feeling forces downwards. And from center of mass, we know that you can replace all these elements by putting a force of the total mass mg at the center of mass here in the center, directed downwards. And this is actually what I do. There is a mass lambda v naught t comes from here times g. And we were thinking about it that it's like it's acting here in the center of mass downwards. And v naught t can be written y. Yeah, that is a 2 here, not the 3. It's still lambda v naught squared over here. Okay, and this is the force. So A is, we are done with that. And now to B, let's calculate the power. And the definition of power, P, equal the derivative of the work. And work is defined by this relation here. Integral F dot product with the dr. And in this one-dimensional problem, it's actually in the we are integrating in the y direction, and force is something we exactly found out here, right? So we're going to perform an integral here. So let's say the limits are y naught to some certain value y. Y naught could, for example, be 0 if we started at 0 here. But let's just say y naught for now. And you put in all these guys here in the integral, and you integrate. And you will get this expression then. And so, okay, that's the work. And now to get the power, you have to differentiate it with respect to time, with t. And then you get this expression here, and finally this one. You see that y naught doesn't matter anymore, because when you take the derivative of a constant, it's just 0. So y naught is a starting constant. Y is not the constant. It could be any y that we like. So we cannot treat that y as a constant. So we get this, and dy dt, what is that? Vy equal v naught t, dy dt equal v naught. So this is how we get this. This is the power. Next, okay, let's look at the mechanical energy of the rope. And we remember it's something like the kinetic energy, half mass v squared plus potential energy. And so the mass is the mass of the rope, mt, and everything is moving with v naught squared. The potential energy is mass times g times the height, right? Yeah, that's for a particle, but for a rope, the height is the center of mass height, i.e. y half here. And mt, yeah, we can get that up here. M as a function of t is here. So we put it in and we make the calculation. We counter this. And then it is said that, okay, we should look at the rate of change of the rope's total mechanical energy. That's very complicated to say it like this, but it means dE dt. Take the derivative of mechanical energy. It's this one here. So we do that. And then this is take the derivative of y squared. That's 2y times the inner derivative, dy dt. And this is the final expression. And when we compare this to that, you see that term here is just the same. because y equal v naught t. So you get v naught squared in t. Yeah, and here there is a difference. Lambda v naught cubed, but here is a half. So remember, power is not the dt. Power is the derivative of the work. That you should remember. Okay, thank you very much. See you later.